Thank you very much, Sergey, for this nice introduction. It's a real honor to be in this colloquium, and having looked at the prestigious number of speakers, I feel, well, honored. So I understand that it's not purely magnetism, but since I don't understand much else than magnetism, I will present you a lot of magnetism, but also something about chemistry and structure. So we start with a playground for with physics interactions. So in my case here, magnetic interactions, and we will do material science. And the material which we will look at is a class of materials which exists since 60 years roughly. So initially they were called carbides and nitrides until maybe 20 years ago a renaissance occurred with the invention of the name max phase materials. So these are materials which can contain a metallic element, a group 4 element, the A, and an X, which initially is carbon or nitrogen, but nowadays it can also be boron. So what is so fascinating about this class of materials? Just look at this cartoon structure here. You see the yellow dots, which correspond to the M element. You see the A element here, the blue dots. And as you know, atoms are always spherical, and so there should be no problem to stack them. But I will demonstrate to you that it's not so straightforward to argue with spherical potentials. So that makes the whole thing interesting. And certainly then you have carbon layers, these little black dots here. This is carbon, which holds everything together and makes it a carbide. And you immediately see that it should be a layered structure with the crystallographic configuration where you have the C-axis perpendicular to the planes and A-axis or B-axis inside the plane. And if you look carefully, you might already see that this arrangement of the atoms is a hexagon. So these are essentially hexagonal planes stacked on top of each other, carbon, A element, metallic element, carbon, and so on. Now, that's a cartoon here. You see the lattice dimensions. Here on the right, you see a cross section recorded with a transmission electron microscope. And you see very nicely that you have, well, atomic columns. So you see here gray atomic columns, white atomic columns indicating larger electron density and so on. And you see a very nice stacking on the atomic scale of these layers. So really like a cartoon looked at from the top to the bottom. So now, since we are here in a physics environment, we can ask ourselves, how can that happen? It's a bulk material. It's not a monolayer evaporated film, but it's really a bulk volume material. When you mix the powders in the correct way, you get crystallites or bigger crystals sometimes, which have this configuration. So you have lamella of these different elements, and I will show you that nowadays this M element or this A element and also the X element can be varied so that we are now at composition ranges in the thousands. Okay, but what does it mean, a playground? So when you look at classical magnets, you might have a picture of such a playground. Well, you have structures, geometrical interactions, crystal fields, you have an environment, and nowadays it might look a little bit dull because it's a classical magnet, and you should have the words topo, nano, and something like that in there to make it more interesting. But I will convince you that classical magnets are very important for our daily energy science life. Now, the new playground certainly is flashy and colorful, and you see that we have max materials, we have MAXenes, and we have high entropy alloys, all of these composites need to be magnetic to be interesting, at least for me, and maybe also for applications in energy conversion. So that's the topic. I will focus on the next material, mention a little bit about the so-called MAXenes. So we go from 3 dimensions to two dimensions and a little bit back. And these colors indicate to you that we also work with many different elements. So for a playground, you see here an indication. So this is a real structure from colleagues Johanna Rosén and Martin Dahlquist, where they mixed molybdenum, terbium, so this is the M element part, with aluminum and carbon. And out of that come these beautiful structures, which you see from the top. You have like a Kagome lattice, molybdenum, terbium, aluminum, carbon. The side view looks like that. You have beautiful atomically layered structures. And this is all reflected here in these colors, which you see here in the diffraction images, in the bright field images, and in the element-specific images. So from that image, I just want to give you or convey you the fascination I have with this material, so that if you imagine that you can now play with these elements, that you can play with these distances, that you have a vast playground for studying magnetic interactions and also using them. So this is, you see, this is all brand new. So this is a new field of research. And from my perspective, I might say physics is just entering that. So with all the knowledge we physicists have, engineers use this material already for a long time without looking into the functionalities so much as we physicists might like to do. Now, when we have a playground, we need players. And as you know, when you have a lot of players, you also need to have some supervisors. So look here in this upper row, we have a joint project with Sergei Ovchinnikov, Sergei Varnakov, Nikita Volkov, and at the Kerensky Institute, which was supported by a mega grant, we built up such a system to sputter deposit such materials with pulse laser deposition, sputter deposition, and MBE. I will not read all the names of the colleagues and students who are involved here, but as you understand now, on a playground with many nice tools, you need a lot of players too. I also want to acknowledge especially Anton Tarasov and Ivan Tarasov, who did a lot of work to design this chamber and made it work by now. So if anybody wants to visit Siberia, there's a perfect machine with plenty of options. You see that on the website to do thin film depositions. My colleague Ulf Wiedwald, who is now also a professor, works in my group. Marina Spasova, Hanna Pasniak already left, unfortunately. And these are the pioneers, let's say, in my group, Yulia Novoselova and Ruslan Salikov, and many students who started the max phase work in my group. Without this great and uncomplicated collaboration with these guys here, Martin Dahlquist, Johanna Rosén, who I consider the inventor of magnetic max phases, nothing would have happened. Daniel Bürgler helped us a lot with scanning tunneling microscopy, for example. And Michel Bassoum, you could call him the Putin of max phases or the Pope of max phases. So he is the one who guides or invented the whole max phase scheme. Okay, so these are the players. And all what I will be presenting you was done in one or the other way by these players. Now, when we want to play, we need, toys in a way. And you see here as a cartoon what type of shapes and connections are available. And I see the max phases in a similar way. We have geometry, we have composition, and we have interactions to play with. And this is indicated here by these arrows. So we can tune the color of these balls, so change the elements. We can tune the distances, the separations of these layers, and then in the end, we can also separate these layers. So imagine, or at this stage, it would be a dream to separate this layer, this top layer here from the bottom layer by removing the blue one, and then you have a two-dimensional sheet. This works, by the way. So now there are different types of compounds. Just to give you a complete overview, we have these type of ternary max phases. You see here n plus 1. So n equals 1 means 2, and here's a 1. Or you have the n equal 2, then you have a 3 here, and 2 carbon or 2 nitrogen or boron, and n equals 3 also. So when you think in terms of 2D magnetism, then you have one layer, you have two layers, and you have more than two layers here, so a complicated structure. And they are all connected by carbon, so covalent bonds essentially. The bonding between the red guys and the blue guys is softer, so that allows us to think in terms of coupling of magnetic and vibronic degrees of freedom. I will show you an example. Well, these are ternary compounds, so you see there are only three colors, red, blue, and black. But you immediately understand that there's a lot of things to play with already. Now, but Johanna and colleagues, they have shown that we can work with quaternary and even quinternary elements and put them into a crystallographic direct position. Martin Dahlquist and other colleagues nowadays calculate, they do a computational screening on the stability of such max phase compounds. And then based on their predictions, the experimentalists try to do it. And sometimes it works. Sometimes in experiment, it works better than in theory. But this nice combination, it's a prototype, an ideal scenario, I would say. We have a new class of material where there's a lot of potential combinations. More than thousands of materials can be investigated. So the guidance by theory is necessary. Okay, so let's go into some examples. Now you see here these so-called 211, 312, 413 types of max phases. At this time, when this was written in 2000, there were 60 phases, but this has really exploded. So when you search now for max phases, the number of citations is increasing dramatically. And I can just smilingly say the students who started with me this project, they have nice citation or impact, or what do you call that, these H factors. Okay, now the menu. That was just introduction. So I will tell you a little bit more about the properties of max materials. Then we go from the three-dimensional stacking to a two-dimensional stacking. We could call that from max to, I don't know how to pronounce that, mix. Maybe in Russian it sounds nicer. So examples are MAXenes as world record capacitors, humidity sensors. And then I will focus on magnetic max materials, which is an upcoming field. So I want to remind everyone of the fundamentals of magnetic interactions. Then we will go to non-collinear spin arrangement, which as you see here, so there are competing interactions. So it's like you're standing in a music concert and people are pulling at all sides on you. Then the structure will depend on the strength of interaction to the nearest and next nearest neighbors. So all of that will lead to non-collinear structures when you're sitting in such a concert. So then, since the interactions may be soft or weak, we can tune by temperature and magnetic field. So energies are in the range of millieV and few tenths of a millieV. We can tune by composition. I show you an example of a huge magnetostriction in such a material. And magnetocalorics I probably will skip, but there are also first indications that one can have magnetocalorics. And certainly that's the nice part. There are always challenges, so work never ends. So let's go here as properties, mechanical properties. So that's why the engineers got interested in that. These max phases are ultra hard. They are used as coatings because they contain a lot of carbon and 3D elements. They are lightweight. So this is a nice oxidation and mechanical resistant coating, for example, in aeroplanes. So they have a high decomposition temperature, so that's why you can use them also in turbines or in ovens. You see here the tube in a furnace, a steel tube, and this was a max phase materials coated tube, so it looks much better. Then you can machine this ceramics material, so it's a ceramic. It's not very good conducting in certain situations. And you can use drill and do mechanical treatment of this material. So that all is summarized here. Decomposition temperatures between 800 and 2300 degrees Celsius due to the carbon bonding. They are heat tolerant, that means also oxidation resistant. They are elastically stiff, so counterintuitive behaviors. They are ceramics, but on the other hand, they are electrically conducting and mechanically machinable. So you could call that a wonder material, but we understand it better. And as we all know, there are no wonders in physics until we understand them. And the best part for the engineers is that they repair themselves. So this is a work here in Scientific Reports of some years ago, where my daughter was involved. So it's it's a titanium aluminum carbide, so a max phase, which has this laminar structure. Then they produce deliberately with a wedge a crack in air, and then they put it in an oven, heated at 1500 Kelvin in air. So you imagine you take a fan, your hair fan, when it makes 1500 Kelvin, and you heat it, the coating, and you see here was the crack, and the crack is gone. A new crack can be opened. You continue heating or heat again. You heal the crack and so on. Even this big crack here, so the scale is micrometer, is healed. Now, how can that happen? Here you see a little bit what is happening in this paper. It's very nicely described. So this titanium and aluminum oxidizes. So it flows out of this laminar structure and closes the gap, the crack. So you have the same mechanical strength as you had before the crack was opened. So maybe a little bit of magic here. But this is for the engineers, it's proven and tested, and it works. Now here's another example, mechanical properties, oxidation resistance. Just look at the alloys here, so which one has as hard alloys, oxidation resistant alloys, nickel superalloys, tungsten alloys, chrome alloys here. And here's just one max phase listed, titanium, silicon, carbon, and you see it beats, at least in this direction, a lot of the conventional materials. It's more lightweight compared to the other alloys here, and it has a higher oxidation resistance. So there are many of these type of graphs nowadays for max phase materials, all demonstrating that this is an extremely nice class of materials where tuning and complete understanding is still missing, or just developing. Let's be more positive. It's developing. Okay, this we had. Well, just an example here. So also in thermoelectricity, you have the max phases beating conventional supercapacitors by orders of magnitude. So thermal power, for example. Other examples here, it's an old list. So electrically and thermally conductive MAX phases. You see here niobium, aluminum, chromium, manganese, the blue ones. I will go into more detail later on. The resistivity is quite good. It's compared here with iron or copper, but it's certainly not, the conductivity is not as good as in copper, but it comes quite close. And the thermal conductivity is also reasonably okay. And what I can add, but I don't show it, all these properties are extremely anisotropic because you have this laminar structure. So in the plane, you have higher conductivity than vertically to the plane. And that might reflect a little bit on what we understand about superconductivity. And indeed, one finds superconducting MAX phases with quite reasonable ordering temperature. So this is also, you see the references are quite old here. I didn't look up what the current status is, but just keep that as a point for your memory that, so we have mechanical, we have electrical, we have superconducting properties, and now we will switch to magnetic properties. So this is a nice starting point. So you have these type of atomically layered, ordered, rare earth IMAX phases. Rare earth means maybe we can create a larger magnetic moment. They have, when you work in topography or topology or in quantum computing, you might be interested that they form Kagome lattices at low temperature. There are many not yet understood observations in spin alignment and also in spin non-collinearities. Okay, so the last point as advertisement for the MAX phases is that you can use an etchant. So in this course, it's HF etching. You remove this A layer and you get these two-dimensional flakes, very similar to the flakes which you get in graphene, but you have terminations here. These terminations offer you, in terms of chemistry, an additional degree of freedom to tune the conductivity and to use them, for example, as a sensor. Here, some years ago, we did use titanium-3 carbon-2, so the, what was it, aluminum, I think, was removed. Then we have this MAXene, and then if we put water molecules on there, we see a dramatic change in conductivity. Just one example. And certainly in terms of magnetism, when you have these guys here with 3D elements or 4F elements inside as a two-dimensional monoatomic layer, so to speak, we can ask ourselves, well, what is the effect on two-dimensional magnetism? Is it useful for spintronics and quantum computing, maybe? Okay, so this is just the younger people here who are still 20 years ahead in their research. They might get interested in moving into this field. So with the MAXenes, it's also an exploding field. So 10 years ago, there was basically no MAXene, and now there are hundreds, literally. So here's just as an overview, like a periodic table, what type of MAXenes one is discussing with a T as a termination. And the T, again, stands for different molecules and different atoms. So by absorbing or chemisorbing certain, let's call that these yellow entities here, you can tune the physical properties of this two-dimensional flake in a chemically stable way. Okay, and this is just written here, at least 100 stoichiometric MAXene compositions and a limitless number of solid solutions offer not only unique combinations of properties, but also a way to tune them by varying ratios of M and X elements. So there are, well, it's, as I said, it's an exploding field. So if anybody wants to work in a futuristic field, go to MAX phases. They find applications in nearly everything, you could say. in energy, catalysis, optical, in electronics, in structural mechanical composites, biomedical applications, electromagnetic shielding, environment, water cleaning, as sensors, and then whatever you can imagine, I might say. So this is just an example, the yearly evolution of the use of this titanium carbon termination and other MAXenes. And there's a nice review here by Yuri Gogotsi from 2019, and there are newer ones also. Okay, so we participated a little bit in that. Anna Pasniak was a postdoc in my group, so working with Ulf Wiedwald, and she did molybdenum carbide MAXenes for enhanced selective detection of humidity in air. So starting out with the molybdenum gallium carbon precursor, MAXphase, by, let me call it a secret procedure, the gallium was removed. And then we had these, or she had that, these MAXenes, flakes. She stabilized them with some, let me call it some chemistry. T is usually some tetra probably, and B is butyl, and A, I don't know. So I would also have to look it up. So chemically stabilized, then you have these flakes. You put them on a chip to have an electrical contact, so it looks like that. You dry that in air, and then you have a sensor for humidity in air. And it's quite special, so it has a reversible detection down to 10 ppm of water molecules. The upper detection limit is 10,000 ppm in humid air, and this covers a dynamic range of 3 decades, so that might be interesting for the engineers. That with one sensor you can cover 3 decades of humidity for detection. Okay, so that's a non-magnetic example. Now let's move to magnetic MAXphases. So you have the M elements, you have the A elements, the blue ones, you have the black C and nitrogen bonds. You can have now a boron, and as I will show you, you can also have iron. And below here, one has also rare earth, and I might say many, many more compositions. And this is mostly based on studies in Linköping, who I say they are the pioneers of all this research, together with Michel Barsoum on the transatlantic side. And I would be happy if the Russian community would help us in Krasnoyarsk to continue with this research. So we want to tune the magnetic properties. Well, first of all, we convince ourselves, you see here again the atomic columns. This is the atomic resolved high resolution transmission electron microscope, fast Fourier transform, high annular dark field measurements, element specific analysis. So you see, especially for the germanium, very nicely with atomic resolution where the germanium is located. So it's like in the cartoon. Now, why do we want magnetic materials? So probably all of you know that that semiconductor-based information processing costs a lot of energy. So we have these supercomputers or these data storage systems, and as one number, 30 Google searches cost as much energy as to bring 1 liter of water to boil. Okay, so maybe restrict our Google searches. So if maybe you do 30 Google searches a day, and then imagine that this costs the energy of boiling water for your tea. Okay, so now when we can solve this issue, maybe with MAXphases, so to reduce the energy consumption, then the ideas would be spintronics or nernstronics or orbitronics. So all kinds of novel ideas, and I hope that I could convince you a little bit that MAXphase materials and the MAXene materials might be a way to use or to develop new materials for these applications. Now, also on the other end, when you look at the demand in tons of magnets, in petajoule for cooling, so magnetic refrigeration, for wind energy, for electric mobility, for magnetic cooling, for automation. So you see here the year, so we are somewhere here, and it's expected the demand for every of these energy consuming automatizations increases. Just imagine that everything or many things in fabrication depend on robotics in the future. Every robot has an electromagnet as a motor. Wind energy requires large amounts of materials, magnets. They should be lightweight for mechanical stability. If all our cars are based on electric drive engines, well, then we need magnets, lightweight magnets, ideally. So max phases might be a way to create lightweight magnets. So I'm giving you now some possibilities what one might consider not only in this fancy fields of spintronics or nernstronics or orbitronics, but just classical bulk type magnets. One example is, which colleagues from Daimler told me, is if the electromagnet in your electromobile car is 2% more efficient than current magnets, then the car will drive 20 kilometers further. So 2% corresponds to 20 kilometers. And then you could consider if you're standing away 18 kilometers from the next electrical uh, um, column where you can charge up your device, you would wish to have this 2% more efficient magnet. So that's something which we are working on in a collaborative research center with the Technical University of Darmstadt. Now, maybe from the junior researcher's perspective, why should you enter the field of max phases? Just look at the number of publications over the last years. For this are all max phases, so till 2021. The magnetic max phases are just starting, you see here, so it's just at the rise, it may be here. So we cannot look into the future, but I would be optimistic that magnetic max phases have a bright future also in terms of making a research career. And certainly with this magnetism, you have the additional secondary functionalities like mechanical stability, oxidation resistance, anisotropic, electric and thermal conductivities. Okay, now we turn to magnetism. So since I'm long time in magnetism, I tend to remind people of basic knowledge. I'm sorry for that, but I take this liberty now. So what are basic magnetic interactions? So we have exchange interaction, we have spin-orbit interaction, we have magnetic dipole interaction, and in an applied magnetic field, we have Zeeman energy. That's all. There's nothing else. So now people might argue, okay, we have Dialczynski-Moria interaction, we have super exchange. So we have all kinds of specialized interactions, new names every 5 years, I might say. But if you go down to the background of these interactions, you, for example, realize that Dialczynski-Moria interaction is a combination of spin-orbit and exchange. So this way you can break down all these new interactions, which are certainly well described, into these four basic contributions to what makes a magnet, or what causes collinearities or non-collinearities in a ferromagnet, in a ferrimagnet, or in an anti-ferromagnet. And or then you invent a metamagnet, which has all kinds of funny interactions and competing interactions. But please, we can argue about that and discuss about that. This is my fixed opinion that there are these interactions only. Now, when we have interfaces, surface effects, so like metal-metal or oxide-metal, oxide-oxide. We have additional degrees of freedom to tune magnetism. So we have enhanced reduced magnetic moments depending on the electronic structure of the interface or the surface. Due to roughness, we have dipole-dipole contributions, spin orbit, broken symmetries, different coordination at the interface at the surface, changes magnetocrystalline anisotropy. We have in multilayer structures, think of the laminar structures of these MAX phases, we might have oscillatory exchange interaction, so Fermi nesting of the electronic structure. Antiferromagnets and ferromagnets combined, we have exchange bias. Then we can, with Dialogczynski-Moria, so exchange plus spin orbit, gives us Dialogczynski-Moria with a little bit of magnetocrystalline anisotropy thrown in. We get in the field of skyrmionics, and then we can play around with spin transfer torque, so electronic structure, band matching, and so on. So it's certainly a very simplified, simple picture, but also already Einstein said one should make things simple, but not too simple. So here I'm on the borderline of being too simple. So then in oxides, we find also fascinating effects. So remember that we have carbides and nitrides, so very similar to oxides in the electronic ionization. So we can have ferromagnetism between two non-magnets. There's ferromagnetism between two antiferromagnets. We can have metallicity at the interface of insulators, and we can find superconductivity. So all that might reflect on the material which we call MAX phase, the wonder material. So, but there's a lot of research left to be done, and I think each researcher here in the community could, if everyone looks at two types of compositions, then we are busy for the next 10 or 20 years even. So what are the challenges? So we want a higher Curie temperature and a high magnetic moment. We want to develop magnetocalorics, so a high entropy change as a function of field or as a function of temperature. For sensors, we might want magnetostriction, so a large volume change in a small applied magnetic field to use these lightweight oxidation-resistant materials as actuators or sensors, and then a vast field which is just beginning to open is spintronics, magnonics, and quantum processing. Okay, now here an example of the problems. So our colleagues in Linköping managed, after theoretical prediction, to grow and produce this molybdenum rare earth aluminum carbon material. Rare earth stands for terbium or dysprosium. You see a 2/3 to 1/3 composition. Which experimentalist would have thought about that? Well, we need computers nowadays. So the structure looks like that, and it really looks like that also in the transmission electron microscope. I just want to emphasize that. So we have the red guys as molybdenum, the light blue guys here, or turquoise, is terbium. So you have these octahedra type of connections, you have the hexagon type of interaction, and then you have aluminum, well, which is not shown here, but this forms the Kagomin lattice underneath. Now, when we do a susceptibility measurement as a function of temperature, the fun happens, unfortunately, only below 30 Kelvin. And you see strong dependencies on an applied magnetic field. So let's just keep it at that. So this looks like phase transitions when you see a cusp in the susceptibility. This reminds the community of magnetic phase transitions. And it seems at 9 Tesla, this transition is mostly suppressed. When we look at the magnetization directly, this is the case for dysprosium, the magnetic moment of dysprosium evaluated from the magnetization curve, you see that as a function of magnetic field, the average dysprosium magnetic moment increases to the expected value, only in large field. So that indicates there are non-collinearities in these rare earth materials. And you also see at the specific heat here, so here's plotted the specific heat in an applied magnetic field of different magnitude. You see here at this temperature range, 15 Kelvin, 15 Kelvin, where we see that a magnetic phase transition is occurring, also the specific heat reacts. So all very nice, but obviously very complex. Now, with neutron diffraction, our colleagues found out, and I will make it short here, that as a function of applied magnetic field, you see here 3 Tesla, 4.7 Tesla, 6 Tesla, and here you see the position of the atoms, and maybe you can recognize the little arrows in there. So you see that the crystal lattice cell structure changes a little bit. So on a larger, so the average magnetic moment on the dysprosium side is very small, in 3 Tesla, 4.7 Tesla, so to speak, it grows, and 6 Tesla grows. Certainly the moment itself does not increase, it's just that the averaged local fluctuating moment is stabilized. Now, so this is a ferromagnetic arrangement. Now, one also finds, due to the layering, an antiferromagnetic stacking. So you see that here, this arrow points to the left, this arrow points to the right. And now this changes as a function of applied magnetic field. You see this becomes smaller and smaller. Well, hand waving, one cannot explain that anymore, I would say. So you can invent some playground tricks to make your kids happy, but we need software and algorithms to really understand what's going on there. And that's currently in process. So we have some models, what's going on, but we always have to remember the competing interactions, and that as a function of applied magnetic field, the lattice structure may move, may change. I will show you a nice example for that. So this is just a summary here. I think I have to go more quickly now. So molybdenum, dysprosium in zero magnetic field. This is this structure here. And in a magnetic field, you can tune the magnetic moment, the average magnetic moment of this material. And certainly this is all happening below 30 Kelvin. So you see here we have a spin density wave at 16 Kelvin, antiferromagnetic order at 13 Kelvin. Well, for applications in real life, except in space, we need room temperature at least. So many colleagues are working on that. Now, just to convince you that what is the option to go to a higher magnetic moment. So we leave the rare earth now and go back to the 3D element as M element, the aluminum as group 4 element, and carbon. And here Ulf Wiedwald grew that on MgO 111. And according to theoretical predictions, it should have been possible, but it never worked with magnetron sputtering. So what technique might he have used? Well, I will tell you in a few slides. But nevertheless, for the moment, let's see what he produced. So you see here a cross-section, again, beautiful lattice or atomic columns, nice structuring as expected from theory. You see here the element-specific scan for chromium, aluminum, iron. So you see here chromium, oscillating as it should, aluminum oscillating as it should, and iron also oscillating as it should. So we can identify also here where chromium, aluminum with lower resolution is located. So, and here you see the trick. It's done by pulsed laser deposition. So this is the first demonstration of a max phase containing iron. And the maximum which Ulf and his co-workers could achieve, or Ulf Wiedwald, his full name, is 4% iron in the max phase. So, and this is the highest iron dopant level obtained to date. As we are, as physicists, we are always optimistic and dream that we can put more iron in there. Now, let's go to the magnetostrictive effect. So now we have a system where we have manganese 2, gallium, carbon, and this shows a large magnetostriction. So you see here we have 2M, so 2 manganese layers, a gallium, and the carbon always in between. Now what is plotted here? We see the lattice plane spacing, so the plane spacing between the M layers, or between the A layers, whatever you prefer, on a relative scale. So note this value here, 10 to the minus 3. And here is the magnetic field applied. So in a field of 0.5 Tesla, we have a magnetostriction which corresponds to roughly 10 to the minus 4, maybe a little bit less, 10 to the minus 5. This is already a large magnetostrictive value when you compare to iron, nickel, or any other conventional ferromagnet. And you see the magnetostriction in the applied field is negative, so the material compresses. And then if you switch, if you increase the field to 3 Tesla, the magnetostriction turns positive. So you have a material which compresses as a function of field and then expands. Well, I think this is fun. This sounds like a pillow to me, magnetic pillow. Now, when and note, this is at a measurement temperature of 200 Kelvin then. Now, when we switch the temperature to 270 Kelvin, we still see here this negative magnetostriction, but weaker. And in larger fields, the magnetostriction is now negative, not positive anymore. So as a function of temperature, magnetostrictive constant changes, and I say dramatically, because now we are here on the order of 4 times 10 to the minus 4 in magnetostriction. So this is 5 times smaller than interphenol, which is known to be the largest, which is known to have the largest magnetostriction. So if you want to have a magnetic actuator at this temperature range, which changes its actuation direction, then you might want to consider manganese gallium carbon, and it's lightweight. So this was published some years ago. So we have a negative magnetostriction and a positive magnetostriction as at different temperatures as a function of magnetic field. So how can one explain that? First, let's look at the magnetic characterization. So here we have the susceptibility at high temperatures, above room temperatures. So we know from other measurement that here in this range it's antiferromagnetic, and then here we have a little bit complicated Curie-Weiss behavior. So here in this range, above 500 Kelvin roughly, it's paramagnetic or super paramagnetic. So there are a lot of open questions still. You see here at 750 Kelvin, we have this funny magnetization jump. Now, when we look at lower temperatures, so up to 300 Kelvin, here's 0 Kelvin, measure the magnetization, we see that in zero field cooled, and field warming, we get a transition around 200, let's say 20 Kelvin, and with a temperature hysteresis of 7 Kelvin. So that might be interesting for magnetocalorics, but I will not go into that. So now, what does that mean? We had, let's say, we were measuring the magnetostriction at 200 and 270 Kelvin. Let me just go back. So 200 and 270 Kelvin is just around this phase transition. So what's going on there? So here we are in what we find as an antiferromagnetic non-collinear state, and here it's more a ferromagnetic state. And these are details which I don't want to go into. Now, what is happening there? So with neutron diffraction, we analyze that in great detail because the result or the phenomenon is just, in a way, very surprising. So here is plotted the lattice change, and here the magnetization. Now, but let's concentrate as a function of magnetic field. But let's concentrate on the direction of the arrows here. So in zero field, at this temperature of 270 Kelvin, we have an anti-parallel alignment, but look here. Here it's parallel. Here it's parallel. And then we have anti-parallel to these guys below here. So it's a structure with a multiple anti-parallel alignment in zero field. Now, if we apply a magnetic field, well, it's easy to imagine that we align these magnetic moments. The lattice spacing here, this is not really to scale, but it indicates what is happening. As you apply the magnetic field, the lattice shrinks along the z-axis. Now, if we are at 200 Kelvin, so below this transition, then we see here that we have a non-collinear, hope you can recognize that, we have a non-collinear alignment of these green magnetic moments. You see here, these two are going to the left. This upper one is going to the right, and so on, but they are not anti-collinear, so they are well, non-collinear, but more antiferromagnetic in zero field. Now, if we now apply a magnetic field, so like putting all the magnets parallel, then the lattice expands and becomes more closer to this lattice constant, but not to this one. So there are still open questions to understand that. So everybody is welcome to give suggestions later on. So I think this is a absolutely fantastic example of competing magnetic interactions. So we have the manganese, we have the gallium, and the black ones are the carbon atoms. And we just look at the manganese magnetic moment. Okay, does the gallium have a magnetic moment? We check that with XMCD. There may be a little bit of polarization on the gallium, but if this has a consequence on the magnetic response, it's open to discussion. Okay, so this is just a summary to see that in a different way. So below this transition temperature, we have this feature. In an applied field, alignment of the magnetic moments, lattice constant expands. If we have an H equals 0, we have this more complicated non-collinear structure, and the lattice is compressed. And this is reflected here as a function of magnetic field. When we are above the transition, it's different. Okay. Now, towards improved magnetic max materials, larger magnetization. So the wish is, or the dream is, to put iron, cobalt, nickel in these mag phases, so manganese, a little bit of iron I showed you already. We want to have this playground of elements which we can use. So starting with the parent compound chromium manganese or pure chromium, gallium C, Ulf Wiedwald tried to incorporate iron as a second M element. So he did that with pulsed laser deposition. So pulsed laser deposition has advantages and disadvantages compared to magnetron sputtering techniques, which are most often or have been used most often. I will not go into the details of the comparison, but I can tell you with pulsed laser deposition, the iron incorporation forming nice laminar structures works. With sputter deposition, so far it didn't work. Also not in other groups. So one has to take care of the lattice mismatch. So that's usually, since we have hexagonal structures growing, one usually starts with the 1-1-1 type of orientation at the interface. Okay, now the theory. Oh, I forgot to put the names here. Sorry for that. So that's Martin Dahlquist and his group. They calculated the entropy of mixing and Gibbs enthalpy as a function of concentration of iron in this parent compound. So here it's pure iron, and the X stands here. Here's pure chromium, and then you add more and more iron. And that's what he finds without going into much detail. So you can calculate the lattice parameters as they change from when you assume a ferromagnetic, antiferromagnetic configuration. And in the experiment, one has here 2 points, as you see. So it's, I would say, the theory is acceptable, not reaching all the ingredients which we have in the experiment. So with Martin and Johanna, we have a nice competition or friendly discussion if theory or experiment is incomplete. So that's very nice to see that we need theory to understand what's going on and to guide us which materials to mix. And so according to theory, it should be possible to go up to x of 0.2, but this doesn't work. So Ulf tried that and Hanna Pasniak, they tried it, but it works with pulsed laser deposition. It works only, what was it? I think 0.4% of iron. Okay, so that's how pulsed laser deposition works. So you have a high intensity short pulse of an electromagnetic wave, which we call laser. This produces local heat here at the target, which is a composition target, usually an alloy target. You flip it from carbon to aluminum to chromium to iron, whatever you want. So it's a very rapid and quick deposition technique for producing homogeneous alloys. So this is quite well established. But for max phases, as to my knowledge, Ulf Wiedwald used it for the first time. So now, whoops, now I'm the wrong slide here. So, well, that's what you see in the end. You see that iron is incorporated. So here's iron. You see what I showed you before, just to put it into your minds, that one can incorporate iron, but unfortunately the magnetic properties are not really improving as much as we had hoped. But anyhow, this is here published in this paper. So pulse laser deposition, as for something for us to remember, could be an innovative or complementary tool to produce new type of max phase films. So 4 atomic percent of iron can be incorporated. Okay, so with that, I come to the end. But before I come to the end, I just want to remind you of the players and of the great collaborations we had. So also the Laboratory of Max Magnetic Materials, which was established at the Kerensky Institute in Krasnoyarsk. So if you want to visit there, well, bring warm clothes, I might say, till you enter Kerensky Institute. And then it's just greater. You have this beautiful machine. If you have nice suggestions for growing films, there's lead, there's reed, there's Auger, there is pulse laser deposition, there's sputter deposition. Collaborations are very, very welcome. And I also want to thank very much to Ulf Wiedwald, who advised us also on the establishing on this lab, to my former students, Julia Novoselova, Ruslan Salikov, who moved on as life goes on. Hanna Pasniak also moved on. So every other 3 to 5 years, we have a new crew. Ulf has established now his own group in my department here. So we have this wonderful collaboration with Martin Dahlquist, theory, Johanna Rosén, theory, experiment, Daniel Birgler, Michel Barsoum, and there are many more which I couldn't list all of here, but these are most important, we also have this established collaboration with Fabrice Wilhelm, with Andrei Rogalev, with Thierry Ruiz, and. So thank you to all our collaborators. Thank you very much for helping us, for supporting us, and in giving us continuously new ideas. Now, I'm almost at the end. So I like that statement from Einstein. Learn from yesterday, live for today. So I live for today and enjoy life. I hope for tomorrow, a better understanding tomorrow. And the important thing is not to stop questioning. So that's why I hope that you will have a lot of questions and suggestions. And what you might want to remember is, well, first of all, max-phase materials are just great. That should be stuck in your head. And so more precisely, they are atomically layered compounds. They are magnetic, maybe metamagnetic. There's a rich playground with many options. In generally, they are magnetically soft materials so far. There's a strong coupling of spin, electronic, and lattice degrees of freedom. The magnetic properties can be tailored by selecting or substituting these M and A elements. And as an additional wide field, you have the 2D materials. And with that, be creative and play, and thank you for your attention.